SVMs or support vector machines are tough to crack as a machine learning beginner. The term support vector machine itself is confusing, and as soon as phrases like soft margin approach or hinge loss pop up, it's tempting to just move on to a more accessible machine learning model. I had a rough time myself getting a real grasp of SVMs, and once it had finally clicked for me, I decided to summarize my key learnings in this video. I hope to provide you with the intuition and fundamental concepts behind SVMs, so you can apply them in your personal projects with confidence. Let's get started. A quick note before we get going. This video is focused on the fundamentals of SVMs. To avoid confusion, I've set aside topics like support vector regression, the dual problem for SVMs, and the kernel trick for a future video. Let's jump right in. Support vector machines are linear classifiers. First of all, this means they are trained to classify data, which is to assign each data point to exactly one out of many predefined categories. And second of all, the classification decision is based on a linear combination of the features. Let's look at an example. We start with the training set, for which we know the true classification of each sample. If you want to think of a concrete case, assume we classify fruits into the categories apple and pear, using the features weight and color. Training a linear classification model boils down to drawing a linear classification border through the feature space, like this. For a two-dimensional feature space, this border will be a line. In the general mathematical terms, the classification border is a hyperplane, which always has one dimension less than the feature space. Once we have trained the model, we can classify new and unknown data points simply by checking which side of the classification border they are located on. In mathematical terms, the hyperplane can be defined as a solution set of a linear equation, like this one. So in other words, the hyperplane consists of all points whose feature vector x fulfill the equation. Note that the vector w defines the orientation of the hyperplane, and the scalar value b determines how far the hyperplane is shifted away from zero. Changing the values of w and b will therefore rotate and shift the plane around in the feature space. Hence, training the linear classification model means to find the best values for w and b, using all the information we can get from the training set. Once we have found the best values for w and b, we can classify new samples by plugging the feature values into the equation. Depending on the sign of the result, we know on which side of the classification border the sample is located and can make the according classification prediction. Support vector machines are a specific kind of linear classifiers. So the big question is, how do they determine the best values for w and b? It turns out there are two perspectives to explain this, and a big part of the confusion around SVMs comes from mixing these two up. Let's have a closer look at them, one at a time. We will discuss a geometric approach to SVMs first, and cover a more abstract perspective after that. My goal is to show you how these approaches interconnect and are just different sides of the same coin. We start with the geometric perspective on SVMs. Given some training data, the main idea of SVMs is the following. We do not only want to separate the two classes with an optimal classification border, but also keep them separated by a comfortable margin. If we have a substantial margin zone around the classification border, this ensures that our classification decision won't be a close call, as there will be no samples too close to the classification border. To put this concept into mathematical language, let's recall the equation for the classification border. By plugging different samples into the left-hand expression, we observed that the further the sample is from the border, the higher the absolute value yielded by the expression. Hence, it is reasonable to define the margin zone as the area in the feature space where this expression yields absolute values less than 1. The location of the margin zone depends on the values of w and b. In particular, note that if we increase the values of w, the margin zone shrinks, whereas a smaller vector w will increase the margin zone. From a geometric perspective, we try to achieve two things when training an SVM classifier: ensuring that the margin zone is as wide as possible, and separating the classes correctly by the margin zone. Given things are so simple as in the current example, we can turn the two goals into mathematics as follows. Widening the margin zone means coming up with a vector w which is as short as possible. For formulating this minimization problem, 1/2 times the squared length of w is used, as this yields a more convenient function to be minimized. As minimizing the squared length will also minimize the unsquared length, this replacement won't change the result. At the same time, the classes within the training set should remain separated correctly. We can put this constraint into mathematical terms using this inequality. Note that the yi denote the correct class labels of the training samples. If you plug the label values into the inequality, you see the constraint requires w times x plus b to yield a value greater or equal to 1 for the training samples of the green class, and a value less or equal to -1 for the purple class members. In other words, the constraint requires that all training samples must be classified correctly and located outside of the margin zone. With this, we have ended up with a constraint minimization problem describing how an SVM classifier is fitted to a training set. This minimization problem is called the hard margin SVM. Hard margin because the classification border and the margin zone do not have to make any compromises and can keep the classes perfectly separated. Note that some training samples ended up being located directly at the margin zone border. Leaving these points out of the training set would lead to a completely different result. As these samples are so crucial for defining the hyperplane and margin zone position, they are also called support vectors. As you probably suspect, we can and should not rely on the assumption that the classes can be separated so easily. Let's see how SVMs can be adapted to handle the general case where this is no longer true. As you can see in this case, there is no way to keep the classes completely separated by a linear classification border. Also, regardless of how narrow we draw the margin zone, some samples either remain in it or are misclassified by the classification border. Recalling the constraint of the hard margin SVM, we notice that we need to compromise, as there is no way to satisfy it completely. In this example, you can see several samples marked in red, which would violate the constraint. Hence, we need to relax this constraint to give the SVM model some leeway when fitting the training set. We do this by introducing penalty values, which are usually named with the Greek letter zeta. Each sample gets its own zeta value, which is used to relax the constraint on the correct location of the sample. You can also think of zeta as the sample's distance to the correct border of the margin zone, in relation to the total margin zone width. Note that we require all zeta values to be non-negative numbers. Ideally, a sample's penalty value is 0, given the sample does not violate the hard margin constraint. But if the sample lies within the margin zone or on the wrong outside part of it, a considerable penalty value is needed to relax the constraint sufficiently. Obviously, we as the users of the SVM model are not happy about the fact that we need these penalty values to satisfy the constraint. To keep this problem in check, we need to modify the minimization requirement as well, to consider the total sum of penalty values there. This introduces a new problem. There is now a trade-off between maximizing the margin zone and minimizing the total amount of penalty we need to pay. This trade-off is represented in the hyperparameter c, which we can use to state our preference. If we choose a high value of C, we put a lot of focus on minimizing the penalty values and do not care so much about coming up with a wide margin zone. On the other hand, a small value of C goes in the opposite direction. We prioritize a wide margin zone in this case, fully aware that this leads to higher penalty values. This new minimization problem is called the soft margin SVM, and it represents the generic versions of SVMs, which is usually implied when the term SVM is used. As before, we can see that the eventual location of the classification border and margin zone is determined by only a few training samples, which are exactly the ones which end up either within the margin zone or directly on its border. In particular, if you imagine we would leave out all other training samples, the minimization problem would still yield the very same result. Again, these samples are the support vectors, which give support vector machines their name. The fact that SVMs eventually rely only on a few samples to define the classification border makes them unique among linear classifiers. With this, we have finished the geometric introduction to SVMs. I suggest to recollect for a second how geometric considerations eventually led us to this constraint minimization problem. Now, let's look at a different way to introduce SVMs, which, in the end, will lead us to the same formulation. This perspective is far more abstract and relies on the notion of empirical risk minimization. To explain this concept in more detail, let's for a second go back to linear classifiers in general. Suppose we have a dataset, have trained a classifier on it, and now it's time to actually use the classifier on new and unknown samples. Recall that we classify new data by computing wx plus b and checking the sign of the result. It can very well happen that this classification rule fails. The predicted class can be wrong, and the samples at hand can belong to the class which has not been predicted. This is exactly what empirical risk minimization is concerned about, to minimize the risk that future samples are misclassified. Let's break this down further. We want to minimize the risk that future samples are misclassified. The problem is, we do not know how future samples will look like, neither what their features will be, nor their actual label. The only thing we really know about is the training set. So we have no choice but to assume that the training set is a good representation of the samples we will have to classify in the future. Under this assumption, we can approximate the risk of future misclassification with the average misclassification on the training set. To quantify this error, we use a loss function. For linear classifiers in general, it's reasonable to assume that the loss function takes two arguments. The first argument is set, which is a shortcut for w times x plus b, the term we use for the classification decision. Please note that set is not the geometric distance of the sample to the classification border, but rather the distance scaled by the length of w. The second argument of the loss function is the true label y. Depending on the chosen classification algorithm, either the labels 1 and 0 or 1 and -1 are typically used. Considering these points, the empirical risk minimization approach translates into this minimization problem, which aims to keep the total misclassification loss as small as possible. However, if we would stick with this formula, we would not care at all about the concrete numbers of w and b. For example, neither the classification border nor the total loss would change if we would scale both w and b by the same factor. To address this, we add a regularization term to the minimization problem to state our preference for smaller coefficient values. As we now face a trade-off between the classification loss and the regularization term, we should also introduce a hyperparameter c, which determines the relative importance of both terms. So far, we have discussed empirical risk minimization by referring only to linear classifiers in general. So how does this lead us back to SVMs? You can probably guess that it all comes down to choosing the right loss function. Suppose we use y equals 1 and minus 1 for the class labels. One simple suggestion for the loss function would be the following. You can see its plot for y equals minus 1 and y equals 1 on the right side of the screen. Consider a sample with label y equals 1. This loss function states that as long as our classification decision is correct and clear-cut, we get a loss of 0. As soon as z drops below 1, the loss is strictly positive, even if the classification decision would still be correct. And of course, for negative z values, the loss increases linearly the further we move away from 0. This loss function is called the hinge loss. If we use this loss function in the general minimization problem, we notice a few curious things. The loss function is always greater or equal to 0, and y times z is always greater or equal to 1 minus the loss value. If we define for each sample theta as the value of the loss function, we can see that by minimizing the total loss on the training set, we have actually minimized the theta penalties we already know from the soft margin SVM. Hence, by using this loss function in connection with the general empirical risk minimization approach, we have reached the soft margin SVM model again. Notice that by using the hinge loss as the loss function, we see how the concept of the margin zone emerges also from this perspective. Samples on the correct outside part of the margin zone receive a loss of 0. Also, we encounter the dynamic between W and the margin zone width again. Assuming we scale B in a way that the classification border remains unchanged, we notice the following. Smaller values of W will expand the margin zone, so more samples will receive a penalty greater than 0. On the other hand, high values of W will move more samples outside of the margin zone, but this will increase the regularization term in the minimization problem. Now it's time to look beyond the scope of SVMs, so we can appreciate the true value of the abstract perspective based on empirical risk minimization. For a second example, suppose we use the labels 1 and 0. To write down the second loss function, let's use the sigmoid function first to turn z into a probability. Now we can define the so-called log loss function like so. In the plot you can see how differently this loss function behaves. Each sample will receive a strictly positive loss value, and it's worth to think about how this will change the behavior of the classification model. And I'm quite sure you already know this model, because only by using the log loss instead of the hinge loss, we have arrived at the logistic regression model. And with that, we have arrived at the end of this video. We have seen that support vector machines can be understood both from a geometric perspective and by using an abstract approach based on empirical risk minimization. Recall that minimizing the squared length of W can be understood either as the goal to widen the margin zone or as a regularization term. Regarding minimizing the sum of the theta values, a geometric perspective would call this limiting the penalties on the support vectors. A more abstract point of view, however, would see it as the application of the empirical risk minimization principle together with choosing the hinge loss as loss function. Thank you for your attention. Hit the like button if these explanations were helpful for you, and let me know any feedback or topic suggestions in the comments. If you want to study SVMs even further, I have put a link to a great lecture about SVMs in the description. Have a great day. Take care.